This presentation is the fourth presentation in this series that we've put together. So we started off in November where we gave a basic introduction to steam and we covered its first principles, how steam's generated. Two weeks following on from that, we looked at the basic design considerations, the thoughts we need to give to convey the steam from the point of generation to the point of use. Before Christmas, we met and we discussed how we use steam for heat exchange purposes and heat transfer purposes. So today's presentation is going to follow on from that, and we're going to look at the topic of steam trapping. So I'm going to start off by giving a very, very brief refresher on the basics of steam. That's primarily for the benefit of anyone that may have missed any of the previous CPD presentations, so you're not left behind. But hopefully it's going to be of use and of interest here, regardless of whether you've dialed into any previous presentations or not. So I've introduced Spirax-Sarco previously. I've explained who I am. My name's Dan Wells and my remit is to support consultants, design engineers, to help them to ensure that a robust design and specification is embedded from the very, very beginning. But we've also got a lot of very useful resources available on our website that can assist you. The one thing I would like to draw your attention to is that little app that you can see right up in the top right-hand corner of the screen. There's a lot of very, very useful, powerful calculators and configurators that you can download to your smartphone, to your iPhone, that you can access via that app. And it's something that is particularly relevant whenever we're talking about the topic of steam trapping itself. So steam traps. Today's presentation, we're going to look at what I believe to be the single most important component that exists on the steam and condensate loop. So last time we met, we spoke about heat exchangers, and that's undoubtedly one of the main reasons why our client will likely have steam on their site in the first case. However, if we fail to size, select, install, or maintain our steam traps correctly, then we're never going to have a steam distribution network that is working efficiently, safely, and providing a consistently excellent condition of steam. So today's presentation is quite a high level, fast paced presentation, but hopefully it's going to provide you with some very, very useful insights that you'd be encouraged to bear in mind whenever you're next involved with either engineering or maintaining a steam system. So let's start with a reminder of the basics. From previous presentations, we should hopefully understand that steam is a gas, and that gas is compressible. So the higher the pressure we generate and distribute that steam at, well, the smaller the volume it's going to occupy. We also understand that there's a direct pressure to temperature relationship with the steam. High pressure steam, high temperature steam. Low pressure steam, it's got a lower temperature. By manipulating the pressure, we are controlling the temperature. We've also explained previously that there's a very, very high heat energy content present within a mass of steam when we compare that to a similar mass of low temperature hot water, for example. And that's got its first principles in the fact that water, the raw ingredient of steam, has got a specific heat capacity of 4.19. That's the magic number that the steam tables and those little apps and configurators are based on. And that 4.19 means if we want to take 1 kilogram of water and increase it in temperature by 1 degree, we need to add 4.19 kilojoules of energy to it. So if we're generating steam at, let's say, 1 bar gauge pressure, then we can refer to the steam tables. We know that steam at 1 bar gauge pressure is 120 degrees. 120 degrees multiplied by 4.19 gives us an indication with regards to how much energy is present within the steam. And when steam condenses, it gives up all of its latent heat energy, meaning there's far more energy flowing into the process than compared to a water-to-water heat exchanger that is only designed to give up 11 degrees. The benefit means, well, we need to generate and distribute far less steam than we would do if we were using water. We also know that steam as a gas is not pumped. It's distributed around the system from nothing more than the pressure within the boiler. Huge installation, capital cost saving and operational cost saving because we don't require those pumps. From the steam heat presentation we gave last week, 2 weeks ago, hopefully you now have an understanding that steam as a gas gives up its heat energy evenly and equally across the heat transfer surface area, helping to keep the speed of heat transfer high. And we also know that because steam gives up its heat energy by condensing, the speed of heat transfer is about 3 times faster when compared to a water-to-water heat exchanger. But as far as this particular presentation is concerned, it's important to remember the fact that steam gives up its useful heat energy, its latent heat energy, by condensing, by changing state from a gas with a large volume to a liquid with a much, much smaller volume. So just a reminder of the steam tables that I appreciate we've looked at previously, but this is a critically important slide and it's worthy of repeating. So the steam tables that are demonstrated up in the top left-hand side of the screen, they give us a lot of very, very valuable, powerful information. And it starts off with the first column. So working away from the left-hand side towards the right, you can see it shows us the pressure that the steam is being generated at. Let's take the example of zero bar gauge. For example, if we're boiling a pan of water on our kitchen hob at home. At 0 bar gauge, we know that the boiling point of water is 100 degrees. And because water's got a specific heat capacity of 4.19, if we had 1 kilogram of water in the pan, we'd need to add 419 kilojoules of energy to bring it up to boiling point. But we don't want boiling water, we actually want steam. And for that boiling water to change state and produce steam as a gas, we need to add a further 2,257 kilojoules of energy to that already boiling water. So when we add the energy in the boiling water to the energy that is required to make it evaporate and produce steam, once that kilogram of water is fully boiled dry and evaporated, that kilogram will contain 2,676 kilojoules of energy. And the final column demonstrates the volume that that kilogram of steam will occupy when it has fully evaporated. The 3 columns in the middle, the enthalpy of water, the energy present in the water. We also refer to that as the sensible heat. Now we can't use the sensible heat for heat transfer purposes. The middle column, the enthalpy of evaporation, we also call that the latent heat. That's the useful heat energy that the process can use. The enthalpy of steam, or the total heat energy, well, it's the other two combined. But remember, that middle column, that is the useful heat energy. Now, of course, if we generate the steam at a higher pressure, those values all change. And that's because at a higher pressure, the water is going to boil at a higher temperature. The water will need to contain more sensible heat, but consequently, we'll actually need to put less energy into that boiling water to then make it change state. So that is for that reason we encourage you to either refer to the steam tables that we have online, or better still, to download that little calculator, as that will help you make sense of all of that information very, very quickly. And of course, if we move over towards the right-hand side of the screen, that really demonstrates the importance of keeping the steam as dry as we possibly can. So if you look at the horizontal line moving across the graph, it really demonstrates the journey that steam, or that water takes, should I say, when we want to boil it at atmospheric conditions or 100 degrees C. Really demonstrates the sensible heat we've got to put into the water before the evaporation process starts, and how much energy we need to put into that water for it to produce dry saturated steam, at which point the evaporation process will end. So if we put slightly less than the 2257 kilojoules of energy into the boiling water to make it evaporate, we are not going to get dry saturated steam. We're going to get wet steam. And the problems that that can cause, as you may recall from previous presentations, wet steam is going to have significantly less energy in it. It means that the process time, the heat transfer time, is going to extend and extend. It means that any moisture that's entrained within the steam can cause problems with erosion, corrosion, and water hammer as it travels around the network. But this presentation is focusing on steam trapping. So whenever we're talking about steam trapping, it's important to understand that if we're distributing steam that's very, very wet around the site, then a significant mass of that steam is going to give up its heat energy to the distribution pipework and condense. So if we're distributing 10,000 kilograms of steam per hour and it's wet, it may well be that we're only actually getting 9,000 kilograms of hour at the process. And we've actually got 1,000 kilograms per hour that's sloshing about the distribution pipework. So it means we need to size and select the steam traps appropriately to drain that condensate and to help keep the steam as high as possible, as dry as possible. So we've also spoken previously about those two relationships we have. We've got the pressure to temperature relationship. If we know the pressure, then we know the temperature. The steam tables tell us that. If we're boiling steam at atmospheric, the temperature of the steam is 100 degrees. If we're boiling water at 10 bar gauge, the temperature of the steam is going to be 184 degrees. By manipulating the pressure, we are controlling the temperature. And similarly, we've got that pressure to volume relationship we spoke about. If we increase the working pressure, we're reducing the volume that mass of steam occupies. Critically important whenever we're talking about steam trapping, because of course a steam trap is a passive device. It means that the pressure of the steam is required to push the condensate across the steam trap. So there needs to be a pressure drop in order for the condensate to move out of the steam distribution network. And I'll come on and explain a little bit more about this in some more detail as we go through the presentation. So hopefully you can appreciate the consequences of not having a steam trap or not having a correctly specified steam trap. And basically that means that if we fail to remove the condensate, either from the distribution pipework or from the process, well, as far as the process is concerned, it means that condensate will back up and flood the heat exchange surface area. And remember, there's significantly less energy in the condensate. The condensate is full of that sensible heat, when actually we want to use this latent heat energy that's present in the steam. So if we don't remove that condensate, the heat exchanger will fail. And as far as the distribution network's concerned, we want to keep the steam space free of condensate, so we're not getting issues with erosion, corrosion, and water hammer. We're not getting excess heat losses, and to ensure that we're not having issues caused by the steam progressively degrading and becoming wetted out. And we also know that certain processes, especially high-end processes in the food, beverage, pharmaceutical, healthcare sector, they could be using steam for direct injection purposes. Or they could be looking to hold the steam at a critical point for a certain process. So quality engineers or quality managers on a client site may wish to monitor the condition of the steam. And when we're talking about the condition of the steam, we're talking about two things really. We're talking about ensuring that the steam is kept as dry as possible, and we're talking about ensuring that we've removed as much of the air and the other non-condensable gases as we possibly can. Reasons being, well, it's simple. When we're talking about steam at the process, at the heat exchanger or a sterilizer or an autoclave, wet steam is going to have significantly less energy in it than dry steam. But it could also be that any moisture that's present in the steam is at risk of contaminating any particular atmosphere. So we also know that air and non-condensable gases can also cause a problem, because if we've got an excess of air and other gases, that can have an insulating effect at the point of heat transfer, meaning we've got a failure to get the correct temperature or the correct amount of energy into the process. So certain industries will refer to a standard, BS-EN 285, in order to benchmark the condition of the steam. Typically, that means that we're going to be looking for the steam to be 95% dry or better. And also we're going to want to ensure that there's 3.5% or less air and other non-condensable gases contained within a volume of condensed steam. But just moving forwards, we've spoken about air venting previously. We've mentioned the problems that that can have with regards to an excess of corrosion. But as far as the process is concerned, it's important to vent air away from the process because it can result in a significant barrier against heat transfer. And if we've got a significant mass of air or volume of air mixed in with a mass of steam, then the insulating effect means we can no longer rely upon that pressure to temperature relationship. The insulating effect at the process, well, it's going to be similar to failing to bleed your radiators at home. So it's important to ensure that we've got air vents located at the process to ensure that any entrained air can escape and be vented away as quickly as possible. And that's probably best demonstrated on this next slide that you can see. For example, when we're starting a process up, such as a jacketed vessel, then it's inevitable that it's going to be full of air. Vacuum breakers, gaskets, air that's entrained within the steam means that it's impossible to guarantee that that solution will be free of air. Now, certain steam trap types, not all of them, some steam traps are capable of venting air away. But they can only vent the air away before the trap and the process is flooded with condensate. So as you can see from the second graphic here, once the steam system has pressurized and pushed the bubble of air past the little condensate offtake that comes off vertically underneath the jacketed vessel, the air has now got no way of escaping. It can't push against that steam pressure to escape through the steam trap. Without an air vent in place, that bubble of air would be trapped and it would occupy quite a lot of the space that was otherwise set aside for heat transfer. So the little steam trap, it's recommended that it does have air venting properties to aid and assist with the venting of air, but we also want to ensure that we've got a dedicated air vent just to ensure and guarantee that once the steam is switched on, it can warm the process up as quickly and efficiently as possible. So we've mentioned that we need to get the condensate away from the process as quickly as we can. We can't use condensate for heat transfer purposes. There's no useful heat energy in condensate, just the sensible heat. However, that condensate is still actually hot water. So one area where we can make good use of that condensate is to get the condensate away from the process quickly and direct it back to the boiler house. Because if we can get that hot water back into the hot well as quickly as possible, then we can utilize that energy as quickly as possible. And if we're recovering hot water, then obviously it means that not only do we have an increase in energy cost savings, but it also means that we'll be reducing the water effluent and the chemical costs. So I just want to look at where condensate is actually formed to give us a better understanding of the steam trap considerations. First of all, over towards the left-hand side of the screen, you can see what we refer to as the distribution losses. In other words, the steam that is going to give up its energy and condense in the pipework itself, even before it gets to the process. And then on the other side of the coin, we've got the steam that does condense when it's actually at the process, at the heat exchanger, where we want the steam to condense and do its job. So when we're talking about the distribution losses, the steam that condenses out in the distribution pipework, there are a lot of different considerations that tell us how much condensate we expect to be given up to the distribution pipework before that steam actually gets to the process. And that can depend upon a lot of different factors. For example, the run of pipework. Is it 20 meters or is it 2,000 meters? Has the pipework been sized correctly? Oversized pipework is going to have a bigger heat transfer surface area, and we'll expect to see a bigger condensate load. Are we producing wet steam in the boiler? If we are, we expect to see more heat loss. Have we got the correct grade of insulation? Have we got trace heating? Is the pipework running indoors or outdoors? So all of these things can affect the efficiency and the condensate load, and therefore affect the steam trap size. But for the vast majority of steam systems, it's typically acceptable to apply a rule of thumb. And that rule of thumb says that on average, approximately 2% of all the steam that is being generated is going to be lost to condensate in the distribution pipework. So for example, if we're distributing 10,000 kilograms of steam per hour, then we would expect that we need to size the steam trap to be able to remove 200 kilograms of condensate per hour. And we can use that information to size and select not only the appropriate steam trap, but also to decide how far apart to site those steam trapping stations. 30 to 50 meters apart is generally the accepted norm. But if we've got a slightly higher load, we want to use one particular steam trap type, then we can shorten the distance and so forth. Now, the thing to bear in mind is that 2%, that's the running load. In other words, that 2% rule of thumb only applies when the steam distribution network is at a nice high temperature already. For example, if we come into a facility at 7 o'clock on a Monday morning and the steam boiler's been shut off all weekend, we fire the steam boiler, we expect more of that energy in the steam to be given up to the distribution pipework. In other words, we expect a greater heat loss. So there's going to be a bigger condensate load to contend with. So we typically double that 2% running load to 4% to allow for what we refer to as the warming up load. So that 200 kilogram per hour needs to satisfy 400 kilograms per hour for the first couple of hours until the pipework reaches a nice high temperature. If we fail to take that warming up load into account, the steam trap would be undersized. And it's at that point that we expect the condensate could start to back up, flood the distribution pipework, and before you know it, we've exposed ourselves to the problems of that erosion, corrosion, water hammer. The steam is getting progressively wetter and wetter, so there's less energy in it, all because we failed to allow for that warming up load. And of course, as far as the process is concerned, well, the purpose of sizing the steam trap correctly at the process is to ensure that the condensate isn't going to back up and flood the steam space itself. So we still need to allow for a warming up load as well as a running load. But depending upon the type of process and how quickly we need to get it up to temperature, in some instances, we may not double that, we may extend it and actually triple that running load to allow for a greater warming up load. So we need to remove condensate for different reasons, at different points of the network, under different pressures. Remember, we distribute steam at a high pressure, but we use steam at a much lower pressure at the process. We expect it to be smaller masses of condensate to remove at a higher pressure, but larger masses of condensate to move at a lower pressure. And so you can appreciate there's no one size fits all. There's no such thing as a universal steam trap. And they're all typically going to fall into one of three different operational principles, which I'll come on to in a couple of slides' time. But suffice to say that there are a lot of different considerations that we need to take on board when we're deciding which type of steam trap that we need to apply. No two steam distribution networks are alike, and there are a number of different factors that we can give thought to, such as the temperatures, the pressures. Is there any vibration of the pipework? Is it a system that has got a high warm-up dependency or a low warm-up dependency? For example, is it operational 24/7? Is the condensate likely to be exposed to freezing or vibration? Are we using it on a site where no yellow metals are permitted, such as oil refineries? Are we using it in a corrosive environment where stainless steel may be required? What's the condition of the steam? A lot of different considerations are going to point us towards one of the three different operational principles. And the three different operational principles use the different physical properties of the steam and the condensate to allow the steam to be held back, but at the same time allow the liquid condensate that's of no use to us to pass back to the boiler house where it can be reused. So one of the first types of steam traps I'm going to talk about today is what we call the thermodynamic, or the TD trap. And this is commonly used on steam distribution networks, the distribution pipework themselves. And they use the flash steam principle in order to operate that little disc. So when we've got pressurized cold condensate, for example, when the steam system has just been switched on, the steam pressure will push that condensate up through the little orifice that you can see in the middle of the trap. And that will operate a little floating disc. But as the condensate gets progressively hotter and hotter, the falling pressure that we expect as that high temperature condensate passes down that tiny little orifice downstream of the disc, the falling pressure is going to generate a small amount of flash steam. And as that flash steam expands and then condenses, that's going to drive that little disc open and close, kind of like a little check valve mechanism. So this type of trap, it's constantly cycling open and closed. And in a correctly sized system, you should hear this trap opening and closing maybe 6-7 times an hour. It'll clack as it opens and then be sucked down as that flash steam collapses and condenses, at which point you'll hear a blast discharge action. So the benefits of the thermodynamic trap, they're very small, they're very robust. They've only got one working part, that's that floating disc, so they're easy to maintain. They don't mind freezing conditions. If the condensate did freeze, once the steam system is switched on and the condensate defrosted, it wouldn't do any damage to the trap. In fact, we wouldn't want to lag or insulate this type of trap, because doing so would actually cause the capacity of the trap to be dragged downwards. Commonly used on distribution systems, we'd never use it behind a process because its capacity is typically too small to satisfy your average heat exchanger. Then we've got the thermostatic traps, and this works on exactly the same principle that a thermostatic air vent works on. It means that we need to locate the trap typically 2-3 meters away from the point that we're removing the condensate from. whether that's a heat exchanger or a steam distribution network. We need that 2-3 meters of pipework to retain the condensate, and the condensate actually needs to be held as a reservoir to give up its heat energy. It needs to cool by anywhere between 5 and 20 degrees. The reason being is we need to have a temperature difference. So if the trap recognizes that we've got cold condensate, it will open and allow the condensate past. But if the condensate gets progressively hotter and hotter, which is an indication of steam being immediately ahead of the condensate, the trap will close, locking in that hot condensate and therefore locking in the steam. So what's the benefit of this type of trap? Well, because it works thermostatically, it's got excellent air venting properties. So if we'd had a heat exchanger, if the process was continually stopping and starting, we'd need to make sure that the air was vented away very, very quickly. Otherwise, the insulating effect could result in a slowdown of the process. A thermostatic trap, that'd be an excellent fit. May well be that we've got a client that's got a lot of flash steam being vented away and lost to atmosphere because we've got such a high pressure drop in that high temperature condensate. Well, by cooling the condensate ahead of the trap, we're minimizing those flash steam losses. Or it could well be that we could use that 2 to 3 meter, that reservoir of hot condensate. Maybe we could take the sensible heat energy out of it and use it for other purposes. For process trace heating, for example, to keep oils or chocolate or any other chemicals, sulfur lines, to help to keep the viscosity low. They've got a perfect purpose in those areas. And then finally, we've got the mechanical trap. It can be a float trap or it can be a bucket trap. Work on the fact that steam as a gas has got a different density to condensate as a liquid. These are excellent workhorses. The major difference between the bucket and the float trap is the float trap's usually got a secondary trap mechanism inside it. So it can work both on the mechanical principle and on the thermostatic principle. It means that we can vent quite a lot of air away on startup. Whereas the bucket trap, it's not very good at venting air away, but it can stand up very, very well to water hammer or a poor condition of steam. But as you can see from the little graphic of the bucket trap, beg your pardon, mechanical traps always retain a little bit of condensate. So if we have got a mechanical trap that's located outside, it could be exposed to freezing conditions. So it would be a good idea to look at lagging or trace heating a mechanical trap, whereas we wouldn't do so with a thermodynamic trap. So as you may expect, it's probably self-explanatory what the effects of an undersized trap are. If we undersize that trap, we're at risk of holding the condensate back and flooding the process or flooding the network. But if we oversize a trap, then the problems that we expect are, for one, an inefficiency, because we've got a bigger heat loss involved in that lump of metal. But it also means that the mechanism can be working far, far closer together, closer to its valve seat, meaning we're going to get a little bit more wear and tear as a result of an excess of erosion with that condensate being sucked across it very, very quickly. So I want to very quickly look at a couple of trap sizing examples. So the application we're looking at the screen at the moment is a process. We're using a steam coil to heat a vessel to warm up some water. So we need to ensure that the condensate is removed from the coil as quickly as possible. We look at the steam load. The steam coil, the process, is calling for 200 kilograms per hour at a pressure of 4 bar gauge. So that means once the steam's condensed, we need to remove 200 kilograms per hour of condensate at a pressure of 4 bar gauge. We can see that the steam trap is discharging to gravity, 0 bar gauge. So we know that the differential pressure here, the motive energy in the steam, is 4 bar gauge. And with it being a process, we know that a float trap is going to be an excellent choice here. Now, every steam trap type, it's got its own sizing curve. And looking at the example or the sizing curve for a float trap, we can see that, first of all, if we take the red line, the red dotted line, that's the differential pressure. That's the 4-bar gauge that we spoke about. We run that vertically up. If we take the green dotted line running horizontally, that demonstrates that 200 kilogram per hour load that we need to get rid of. But the yellow line that sits above it, that demonstrates that we've now doubled the running load to allow for that warming up load that we spoke about. So you can see that takes us from what would otherwise be an FT 1410, and we've now increased it to allow for the additional load. And in this case, it means that we've sized utilizing an FT, that stands for float trap, 14, that's the maximum pressure rating of the casting, 4.5, that's the maximum differential pressure. In other words, it's really demonstrating the importance of taking that warm-up load into consideration. As far as the thermodynamic trap's concerned, well, we're going to be distributing steam almost constantly. Your processes can be stop-starting all the time. But if we're distributing a load of, say, 8,000 kilograms per hour at a pressure of 8-bar gauge, then again, we're able to determine the condensate load that needs to be removed. But you'll notice that we've got another little trap that's in parallel here. It's not just the thermodynamic trap. Certain applications could have a low temperature thermostatic trap. And the purpose of this dump valve or temperature discharge trap is to get rid of any cold condensate that may be present if and when the steam system is shut down. It dumps it to waste very, very quickly, and it prevents the erosion, corrosion, and water hammer issues that we've spoken about previously. And remember, it's only low temperature condensate we're dumping to waste, so there's no great energy loss here. And once the temperature of the condensate builds up to a point where it can be effectively recovered, the dump valve will effectively lock closed, and the management of the hot condensate will then be taken over by the thermodynamic trap. So, two things to bear in mind with thermodynamic trap sizing. It's really demonstrated again on the sizing chart that we can see here. If we take the load, 8,000 kilograms per hour, well, 2% of that load is 160 kilograms. So if we take the 8-bar gauge differential pressure shown in red, if we run the green line, 160 kilograms per hour across horizontally, you'll see that if we have got a dump valve fitted on this assembly, we can use an L or a low capacity trap. Whereas if we don't, it therefore means that the trap is expected to handle the higher warming up load, and therefore we need to double that 160 kilograms per hour to allow 320 kilograms per hour of condensate to be discharged. But of course, if we can't use those sizing charts, we can refer back to those useful little apps that we've spoken about. So there are a lot of different applications where steam traps can be used in different applications, different processes, because they could be expected to remove condensate for different purposes under different loads and different conditions. And in addition to removing the process losses that we've already covered, it's also important to ensure that we're removing the condensate from the bottom of steam separators to remove that entrained moisture, not only to keep the steam as dry as we can, but also to protect control valves and pressure reducing valves from the effects of erosion. So we want to ensure that we've got a steam trap located underneath the separator. We also want to ensure that we're trapping ahead of any control valves or isolation valves. The reason being, if that control valve or isolation valve modulates closed, any steam that's held ahead of it will condense. And then once we open that valve again, that condensate could be released with a lot of energy. So it's important to trap the steam at those locations as well. Now, we've identified that steam's a gas, condensate's a liquid. And we know that when condensate falls in pressure, then there's got to be a loss of energy. But whenever we're sizing the condensate pipework itself, the first thing we want to look at is what the condition of the condensate is at that point. So where we can see the downward pointing arrow here, it tells us that if we've got a process that's condensing 100 kilograms per hour of steam, we know that the pipework needs to be sized to remove 100 kilograms per hour of condensate. Now at this point here, all we really need to do is to take that 100 kilograms per hour and multiply it by the appropriate warming up load. So if we've got a sensitive process, remember, we might want to double that running load by 3 to ensure that we're always draining the condensate away from the heat exchanger, the jacketed vessel, and it's never going to back up and cause the process to slow down. But it's at this point here, between the process and the trap, the condensate's a liquid, but it's under pressure. So there isn't any fall in temperature, there isn't any fall in pressure, there isn't any fall in temperature. We've got a single phase liquid at this point here. So the little chart over towards the right-hand side of the screen, that's really intended to demonstrate that we can use water sizing methodology here to size the condensate pipework. As long as we've allowed for that factor, that multiplication of 3, to allow for the condensate to drain away, we've sized the pipework correctly. Now, it's downstream of the steam trap. This is where we see the problems. So remember, at this point here, condensate's a liquid. It's a single phase. It's under pressure. And because it's under pressure, taking the example of 7-bar gauge, well, the steam tables tell us that the sensible heat in condensate at 7-bar gauge is 721 kilojoules per kilogram. So if we've got a fall in pressure downstream of the trap, which we actually need to have in order for the steam to move the condensate across the solution, but let's say we've got a fall in pressure from 7-bar gauge to 0-bar gauge. Well, the steam tables tell us that at 0-bar gauge, condensate can only contain a sensible heat of 419. So that fall in pressure means the condensate has got to lose 302 kilojoules of energy very, very quickly. How can it do that? Well, it can only do that by a phase change. A certain percentage or a certain mass of that liquid condensate is going to change state back to total heat energy. It's going to move from sensible heat to total heat. It's going to change state from liquid back to steam again. We call that flash steam. The problem is that phase change is going to result in a huge expansion very, very quickly. So we need to allow for the pipework to be sized to contain that rapid expansion very, very quickly. If we didn't do that, we'd get a lot of banging and vibration and damage to the pipework, and we'd get a huge back pressure placed on the trap, holding that condensate back. So this shows you a typical condensate pipe sizing chart, and that allows us to take into account the fall in pressure as well as the mass flow rate, because that will then allow us to calculate the amount of expansion that is required. So for example, if we took the horizontal line, the 100 kilograms per hour horizontal line across, you could be forgiven for seeing how an installing contractor could fall into the trap of massively undersizing a condensate pipework. But in actual fact, we'd have to take the dotted line going up diagonally and sizing somewhere between a 20 and 25 mil. So please consider condensate a biphase and not a liquid. Condensate is a liquid, but only at a stable pressure. Other good methodology, we want to avoid corner cutting. We want to avoid bringing multiple processors together with one steam trap. It's good working practice to ensure that every process has its own dedicated steam traps. Processors will work at different rates. They'll condense steam at different temperatures, different pressures, and one process could adversely affect another. So please avoid what is referred to as group trapping. It is acceptable to bring multiple traps together into one common discharge line, as you can see on the image above, but we do need to employ the correct methodology to ensure that the condensate pipes have been sized to step up in accordance with not just the increased mass flow, but also the volumetric flow caused by that expanding flash steam. Good news is that's one of the calculators that I've referred to on one of those little apps. So steam traps, well, they are mechanical devices and they can fail. When they fail in the open position, it's self-explanatory. We've got a huge loss of energy, and that's generally emphasized if we just look at the various flash steam vents around site. It tells us that we've got a problem with a huge loss of energy. It means that we're not getting the condensate back to the boiler house. The raw water costs, the energy costs, and the chemical costs are going to escalate. And we can keep an eye on trap condition if we monitor the condition of the traps periodically. And just look at this statistic here. If we've got one steam trap operating on a site 24/7, 50 weeks per year, if we're distributing steam at 6 bar gauge pressure, just one steam trap, a 1-inch steam trap, can be responsible for the loss of over £9,000 worth of lost energy per year. Now, if we've got a site where the cost of steam production is significantly higher, if we're distributing steam at a higher pressure, and if we've got a greater number of failed steam traps, then you can appreciate how those costs can escalate significantly. But of course, when we've got a steam trap that's failed in the closed position, then the implications are different. If it's a trap that's located behind a process, a heat exchanger, well, the process could stop, production could stop, and that's got a completely different metric. But on a distribution line, if a trap fails in the closed position, the condensate could back up, and it could affect the condition of the steam, the heat losses. It can result in erosion, corrosion, and water hammer. That's a little bit harder to identify, but the impact is going to be just as severe. So it's important to monitor steam trap condition routinely. We can do that in a number of different ways. For example, our clients can hold a periodic steam trap audit. An engineer will routinely examine the system for failure, whether that be open or closed. But in addition to that, they can check that the correct trap has been installed, it's been sized correctly. That'll be reported back typically annually, and that is generally quantified with regards to understanding the return of investment that can be enjoyed in fuel savings if the appropriate repairs are taken place. Or for more sophisticated systems, it can be done automatically in real time by means of having an automated system sending a signal remotely over Wi-Fi in an intrinsically safe environment. And that signal can be sent to a production manager, utility manager, maintenance manager, so they can get an understanding of the overall integrity and efficiency of their steam trap population, and they can get a signal in real time to advise them when any modifications are required. So moving forwards, we've spoken about the traditional steam trap station to date, And traditional steam trap stations, they require a number of different ancillaries, isolation valves, strainers, check valves, that all need to be close coupled together for the correct operation. And of course, that can bring around a number of different challenges. One such challenge is that, well, there are a number of different leak paths that can result in a trap failure or a trap inefficiency. But by bringing all of those components together into one common casting, it means that we're able to eliminate 10 of those previous leak paths, meaning that a trap is going to work far, far more efficiently from the off if we've got that one common casting. But other benefits mean that it means we've eliminated the risk of galvanitic corrosion if we've got materials of dissimilar metals. It's cost effective to make it out of a high grade anti-corrosion stainless steel material. It means that we've got a smaller footprint for ease of installation, and it means it's less likely that anyone's going to install the solution incorrectly with the components in the wrong configuration or in the wrong flow path. It also means that it's far, far safer for our clients to be able to lock off and perform any routine maintenance with a minimum of downtime. So the only reason I mention it is traditional traps and modular traps are still available. It's just recognizing what the client's requirements are. The vast majority of end users will typically have one or the other written into their site standards. It's just so that you can recognize the difference between the two if you ever come across them. And as far as trap standards are concerned, all trap manufacturers have got a number of different standards to adhere to. I think that perhaps the most important one is ISO 7842 at the very, very bottom. And that basically ensures that all trap manufacturers are benchmarking the flow capacities of the traps in exactly the same way. So thank you very much for taking the time to go through today's presentation with me. I think the two things I'd really like to leave you with today is understanding that we do need to allow for both a running load and a warming up load to correctly size a steam trap. And please also ensure that when we're sizing the pipework upstream and downstream of a steam trap, that we give thought to what the condensate is. Condensate is a biphase when it's exposed to a fall in pressure. So thank you once again for joining me on number 4 of our series of CPD presentations. What you'll notice at the very bottom of the page is we've got a late entry. We've added an 8th CPD presentation at the request of a number of previous attendees, where we're going to look through the future of steam with regards to solutions that are really coming up in the elevator to address sustainability challenges that our clients have. So we've put that in for the 10th of March, and hopefully that'll be of some interest to you. As previously, if you want to drop me an email or message me, I'd be happy to send you a PDF of the slide pack and an attendance certificate and address any questions that you may not want to ask in a public forum. But failing that, I'd just like to ask Brian to open up the microphones and let me know if any questions have come in over tonight's chat function.
Okay, thanks, Dan. As always, absolutely brilliant. A couple of little hiccups with sound quality. Hopefully that didn't spoil everybody's enjoyment, but it sort of backed off a little bit after about a 5 or 10 minute sort of glitch period. Got a couple of questions. The first one of a non-technical nature, which was somebody was after seeing the previous lectures on YouTube. They're not actually on the IMechE YouTube. They're on Project Solutions account. But if you just go onto YouTube and type in Project Solutions Steam Lectures or Steam Lectures Project Solutions, I've just done that and it took me straight to them. So hopefully that'll solve that problem. James has asked if it's okay to route condensate lines uphill. If so, will there be a need to put a drain on the low point of the condensate line, or is it okay to leave flooded during outages?
No, it's okay to leave. Well, It's okay to leave flooded, providing it's not going to do any prolonged damage. If it's going to be exposed to freezing conditions, then it may be advisable to drain away across one of the thermostatic dump valves I referenced previously. Running condensate uphill, running condensate uphill, yes, it can be done. Steam at 1 bar gauge pressure of steam has got enough motive energy in it to lift condensate 10 meters. So providing we're talking about the condensate pipework downstream of the steam trap, and we're not talking about running steam counterflow, in other words, running the steam uphill and the condensate draining back downhill counterflow, providing I've understood the question correctly, if we're just talking about the condensate, yes, it can run uphill.
Okay, thanks, Dan. Hopefully that answered the question. Kenneth's asked, thermodynamic drain traps also work for compressed air, question mark. I know there is a product called Aerodyne from Spirax, which is designed for compressed air. How does it work, since compressed air doesn't condense?
Very good question. And as far as the compressed air side of things is concerned, that is a question that I'm going to have to look into and get back to you. And if Kenneth wants to drop me his email details, I'll kindly answer that question once I've spoken to one of my colleagues who work on the compressed air side of things.
Okay, thanks, Stan. Brendan, are you coming across a lot of sites that have tried fitting orifice type traps? I know Spirax used to take a dim view of them previously due to safety concerns.
That's a very good question. An orifice trap does have its place. I'm not going to call it a trap because, as we've already mentioned previously, hopefully you can appreciate the difference between the running load and the warming up load. Now, an orifice trap is basically a fixed hole. So it can either be sized on one condition. It can either be sized on the warming up load, or it can be sized on the running load. It's either going to be oversized or undersized. If it's oversized, there's a loss of energy. If it's undersized, we're holding the condensate back, which could have a problem on the distribution network, or it could have a problem on the process. So we're not saying that an orifice trap doesn't work. We're saying it will only work efficiently and correctly if we've got a stable condition where the process is producing a stable amount of condensate 24/7, 365. And if you really do want an orifice trap, bear in mind it's nothing more than a hole. It'd be far cheaper just to get a needle valve, and of course you can regulate with a needle valve. So I'm not going to rubbish an orifice trap. I'm just going to say the applications where it would work efficiently are going to be limited.
Okay, thanks, Dan. There doesn't appear to be any more questions. Thank you to the 48 people that connected into us this evening. Fourth of our series of 8 lectures. Next one's in a fortnight's time. If you need to contact Dan, his contact details are on the screen. If you want to find out anything more about Project Solutions, grab me on LinkedIn, or I think my email's on the NEAU website. A big thanks to the IMechE who helped us make these things happen. And obviously a big thank you to Spirax Sarco, who put a lot of energy, pardon the pun, into this sort of stuff. And it certainly helps with continued professional development. So have a great evening, everybody. Hopefully I'll see you, or you'll see me, and we'll be able to engage with you in a fortnight's time. Thanks very much, and good night. Stay safe.
Thank you. Thanks. Good night.